Okay, so I'm going to talk about building a Git reverse proxy in Go for Caddy. My name is Gabriel Mazetto. You will find me online as Brodoc in many social networks and online communities. This is my blog. This is where I'm going to post the presentation slides after it, and also the source code. I work for GitLab. GitLab is your solution for Git hosting, continuous integration, continuous deployment. We love Kubernetes, we love DevOps, and we also do that version control thing. So this talks about Git and its internals, and it's also a tiny bit of Go. And I will not teach you how to Git, so you don't need to switch to the other presentation. Yeah, thanks God. I have to introduce you to a lot of concepts before. This will make the whole process a little bit easier. It will make it easier to understand the code and also the decisions that I had to make. Oops. So, please raise your hands who use Git here every day. Okay? I'm assuming that the other people are watching the other presentation. Because no one in 2017 will not use Git to do their work. Otherwise, they will probably be using COBOL or something like that. So what Git really is, you know that this is the Git that you use, but what it really is. It's not a single binary file, just to start. If you try to look at the Git installation, you will find that it's actually 76 executables. What? Yeah, Git follows the Unix philosophy of specialized and minimalist and modular small tiny files that work together to provide the final outcome that you want. So you have very tiny process running and cooperating together. This is pretty much how the whole Unix work. And it's not always, it's not all of the files binaries as well. We have here, for example, PowerScript and also shell script. This means that if you want to customize Git itself, you can even write pieces of it in Ruby or JavaScript. Next question that you may have, where is my code really stored? Git has this concept of an object database that it calls it ODB. And it's really is a database, and it's also an interface for other types of database. For example, with the ODB interface, you can have you can implement even an S3 backend, or you can plug it to a NoSQL database. And this is available in the source code. You can work with this with the Git-C implementation and also with the libgit2 implementation. It is the implementation that most of the scripting languages like Ruby, Python, and JavaScript use to interact with the repository itself. So how does the ODB backend work, the one that you use today? This is an example of the Git object. Let's try to see if this works. Oops. Bad idea. Okay. Again. Yay. Okay. So yeah. Okay. The connection is not very well. I will try to just point with the hands, the low tech. So on top of it, you have the git log command. You see that there is this this first argument, this first token, which is commit. This is the type of the object. Here is the key of the entry in the database. It's a hash using SHA-1, and here you have the actual content of the database. So it's not really a key value store because you have many other keys and multiple values. It's actually a non-cycle graph data structure. But what I just showed to you is just the pretty version of the Git object. This is just like, this is the front end. So how does the Git commit object is really stored on the disk? We can see this with the git show half command. It shows the half of the object, and then with the git cat file, you can see how it is stored on the disk. So it has reference for a tree and for parent and the other stuff that you just saw. So what is the tree? This is the tree. So the tree is like a directory. The tree is not only pointing to files. It can point to another tree and so on. So for example, if you have a project with multiple folders, you have here multiple trees being pointed by the first tree. The tree itself includes the same amount of blobs, which are files on the disk. It has the permission of each file and also the name of each file. Each blob has the content of the file. It's not a direct comparison with the file stored on the disk. For example, if you have 10 equal files, they will have the same hash, and they will be stored as a single item in the database. And this is important because you want it to be fast and you want it to be resource aware. So you don't want to waste disk space. The next item is the parent. So this is a graph. So you have items pointing to the next one or to the previous one. And it's just another commit. So for you to have a visualization, this is what we just saw. So we have the first commit, which is actually the last one. It points to threes and to blobs. And the next commit also points to another three and points to other blobs. But you can see here that they are both sharing the same blob because that file haven't changed between these two commits. Next question. How is the hash generated? You heard me talking about that the hash is based on the content. It's kind of. This is how you generate the hash. So you have the object type, which is commit. You have the size in bytes. Then you append the null character as a separator. And then you append the object content. So for instance, you may have known that SHA-1 is not as safe as it used to be. there is already a proof of concept of a collision. But as you can see here, it's not very easy to do that, because it's not just the content. You have to match the same size, otherwise the hash will be different. This is how you make it from the command line. So I'm using here printf, which is print formatting. You have the commit token. It will replace the size with that WC minus C and the whole gitcat file, and then it will append /0, which is ASCII code 0. It's the null character separator. So that's how you will see it. You don't see the null byte character actually, but I'm just pointing where it is on the memory. Yeah, this is the whole thing. So commit, the size, and the content, and this is what is hashed. And as you can see, it is the same hash. So you can run this in your house with your hashes just to know that I'm not lying to you. Yeah. Let's talk about protocols. Syncing your Git repository can be interesting. There are a few ways that you can use to sync your repository. You may know a few of them, but perhaps not all of them. You're seeing here 6, but it's actually 5, and I will explain. You have the Git protocol, you have the SSH protocol, and the other 3 are based on HTTP or HTTPS. So let's talk about the Git protocol. It's a read-only protocol. It's the first one that was invented. It was invented by Linus Torvalds, so it could deliver the Git repository for Linux. It has no permission control, and it is very efficient, and it's actually very simple protocol. It's a line-based protocol. It's text, and most of the part is text. It has a binary mode, and it looks like most of the earlier protocols of the internet, like SMTP or even HTTP. You make the request in text mode, and then switch to the binary mode and get the content that you asked for. To access the Git protocol, you run the Git daemon, which is available in all your machines. It is installed with Git. You just need to use the base path argument to point where the request will start. And you can clone from that address. For example, if you are in a local network, you can share your repository with your peers with just using Git daemon. The next one is the SSH protocol. Here is an interesting thing about the Unix philosophy. The Git itself doesn't implement any custom open SSH server. It uses the one in your machine and a few commands. One of those 76 that you saw earlier. These are the two ones that it uses. The upload pack is when you're pushing, and the receive packs when you're pulling, or it's the other way around. I just don't remember exactly. I think it's the other way around. When you're pushing, it uses the receive, and when you're pulling, it uses the upload. This is probably one that you have never heard before. This is the webdav protocol. This is a very old protocol. You can think of it as a FTP over HTTP. So it has all the permission controls. You can send files, you can receive files. It's a very earlier version of the REST protocol, but just for files. There is the dump protocol. It's called dump because it doesn't require any custom script on the backend. It's over the HTTP, as I said before. It is also read-only. It's highly cacheable. You will see after why. And it requires you to change the way that you store your repository. So if you have a repository that you want to expose to the internet, you can use Apache or Nginx, put it into a public folder, run this command inside your Git repository, and you can clone. It's out there. You can add permission control because it's on your web server. If you implement any kind of permission control inside Apache or Nginx, like adding a predefined user or password, you will be protecting your repository. So this is really nice. The other one is the smart protocol. So here is where the things starting to get interesting. The same Git that you have in your machine also have a implementation of the smart protocol, but it's based on fast CGI, which most of you probably don't know how to use, but it's available in any web server. You can start Apache pointing to a fast CGI file, and it will execute and enable the smart protocol. The same for Nginx and all the other servers. And behind the scene, it uses the same two files that the SSH protocol uses. And it's doing RPC over HTTP. So let's talk about Caddy. Caddy is a single binary HTTP server. And this is really cool. You can run your web server just by calling the Caddyfile from your terminal and passing in as reference a CAD file with all the configurations. And it's not only a HTTP server, it is also a DNS server at the same time. And this is also extendable. You can implement other types of server in the same binary file. It is secure by default. It uses Let's Encrypt. So if you configure your file, your vhost, starting with HTTPS and a public available domain, it will handle all the necessary steps to get a Let's Encrypt certificate. It will renew for you automatically, and it will handle all the transactions, all the specificities of it out of the box. It also has man-in-the-middle, attack detection, and many other advanced features. This is just an example of the syntax of the Caddyfile. So the first thing is the label. For the HTTP server, this is where you put the address of the vhost, and then you have directives, which you can imagine it as I'm enabling a plugin with this configuration as the argument. I'm enabling the other plugin with that configuration as argument. And this is an example of a full Rails Caddyfile version of a reverse proxy. you have on the top the vhost address. I'm defining the root folder. I'm defining rules for log rotation and also log retention. I'm pointing a proxy of the root file of the root folder to two different instances. So I'm doing a load balancer here using round robin. And the last thing that I'm defining there is that this is a transparent proxy. So it will add all the headers for forwarding the IPs that your Rails application can use instead of the reverse proxy IP. Now try to do this with Nginx. It's a lot of configuration files. And you will probably make mistakes during the process. Let's try to build up some plugins for Caddy. This is where the Go code starts. There are a few types of plugins. As I said before, Caddy has different types of server. So one of those types of plugins are server plugins. It has HTTP middlewares and some other stuffs that you can intercept in the middle of a request. For example, you can implement your own man-in-the-middle code inside the web server as a plugin. We are going to extend the Caddyfile. So we are going to add a new directive. So this will enable us to configure our plugin and also implement a HTTP middleware. If you worked with Ruby before, this is like adding a rack middleware to the framework, but we are doing this on the web server. I will switch now to the code. So we are going to start with the boilerplate. Let me just make the transition here. Okay. Okay. Let me explain first what I did here. So this is my plugin folder. I name it as Caddy Hello World. So I'm going to implement a Hello World application on the web server, and it will accept the name that it will say hello as a parameter on the configuration. Okay, so I have the setup file. It has the init function. This is the two things that we need to configure for the web server to inject the plugin into the middleware stack. So first, let me you start with register plugin. You give the name of the directive here. You define the server type and the first action that it will call. So this is a callback registration. We also add this to the directives. This is one of the things that I didn't actually like about Caddy. To develop a new plugin, you have to edit the source code of Caddy. You have to add an import there, and you also have to add a directive there. So when you're developing it locally, you can do this dynamically with the directive registration. But to release the code, you have to put this on the Caddy source code itself. Just a second. Not this file. Let's try the terminal. Okay. So these are the changes that you have to do on the Caddy source code itself. You have to add the import for all your plugins. It has a service on the website that does this for you for all the official plugins. So you can download the binary with all the plugins that you have previously selected. But if you're doing something custom for your company, you have to do this yourself. Okay, this is the Caddyfile that we're going to use. It has the vhost configuration here. It's pointing to a root folder, and I'm using 2 directives with 2 different arguments. This is the normal boilerplate. You get the configuration. You initialize some data structures here. Then you go through all the configurations on your Caddyfile. You assign the values that we covered there to the data store. Then you define the initialization code of your middleware. And at the end, you add your middleware to the whole run stack. Let's see how the middleware code looks like. Okay, this is the data structure that I'm using. So I have here an array of names, and I also have a pointer for the next handler. As this is a middleware for HTTP, I'm using server HTTP, but this is not the server HTTP from Go. It has this extra signal code. And I will tell you later what it is. So when the request comes to the server, I will match any request that it starts with /hello, and I will print hello with all the names that were previously configured. And I will return the first code as 0, which means to the other middlewares that we have changed, we have written to the request. If the request doesn't go to /hello, I will pass to the other HTTP middleware. So there is an order where for all the HTTP middlewares that is bundled, and the very last one is the one that delivers a static asset to the end user. So when you enable the other middlewares, they will either intercept the request or they will pass to the next one. Let's try to run the code. Oops. Okay. Let's open the web browser. I will try first without the correct request. So it will return 404. And if I try with /hello, I get all the code that I just written. Okay, so next one. So with this, you have an idea how the whole boilerplate thing works. Now let's try to do this for Git. Okay, it is the same boilerplate here. I'm registering the plugin as Git proxy. This is the name of the directive. It will point to the first action. Will start with the setup function. And here I'm initializing a few other parameters, like where is the Git command binary located on the disk, and initializing the possible paths that you can pass to the plugin. So let me first show you the Caddyfile. So you can understand what we are configuring here. Okay, I'm using the Git proxy directive, and I'm saying to my plugin that I want it to handle requests for lita hangout.git as a smart Git proxy request. So I will show you how the Git dump synchronization mechanism works before, and then we are going to dive through this request and see how it goes with the smart synchronization protocol. I think I can do this from here. Okay. Okay, on my Git folder, that is the root configured on the Caddyfile, I have two repositories. There is the lita hangout and the lita queue. I configured my middleware to handle only the Lita hangout. So when I try to clone with LitaQ, it will be just a plain simple proxy, reverse proxy of static files. Okay, it worked, but let's see what happened behind the scenes. Okay, the first request that the Git client will make is this one. It will ask for /info/refs, and it will pass service and the name of the file of the executable that it wants you to run on the background. But this is the dumb protocol, so we are just returning the content of info refs that we prepared previously by running the update server stats. After that, it switched from smart protocol to the dumb protocol, and it started to asking for all the objects on the repository and getting one by one as just a normal HTTP gets. And I can show you all the objects here. Okay, they are all here. So it first tried to get the objects, then it switched to get the pack files. And it succeeded with the pack files. Okay, now let's try to get it using the smart protocol. Okay, you see that you have a different output here. What happened behind the scenes was just these two requests here. So it first tried to do the service discovery. My code answered the correct output, and then it confirmed that we are going to use the smart protocol. So the next transfer was just doing RPC over HTTP. Let's see how it works on the code. Okay. The first route is for the service discovery and the protocol enablement. It's being handled by the handle info refs handler. Let's see the code. Okay. I'm querying for the service query parameter on the request. If it matches with Git upload pack, if it doesn't match with Git upload pack, I return a status forbidden. This is on the Git specification. If it doesn't include anything, I pass it to the next middleware handler. But if it actually has the Git upload pack as a service parameter, Git expects that I set the content type as this value. So it's Git upload pack advertisement. I also have to print a pack file aware protocol. This is I will show you. This is interesting. So the packet write is kind of similar how we generate the hash file. So we have the 4 initial bytes are the size of the line. It is after that the line-by-line protocol. So I'm answering this line, service git with the service name, plus the first 4 bytes as the line size in bytes. After that, after the initial request, I'm piping the request to a Unix file, which is the git upload pack. So everything that the git is writing to the connection buffer is passing through the web server to a Unix command, a Unix binary running on the server. So this is the git upload pack. They do all the RPC command requests and response, and this is what generates this output. So summarizing, the dumb protocol is just plain HTTP requests, while the smart protocol, we are piping your request to a process running on the server that are receiving commands and replying. So this is synchronous, and this is a RPC implementation. Okay, so you just learned a little bit of how the Git internals work. I showed you a little bit about Caddy, which is a very tiny web server, and I tried to give you an insight on how you can create plugins for it that may be useful for you on your day-to-day. If you have questions, we don't have enough time anymore, so you can find me outside. I also have GitLab stickers, so please come talk to me. Thank you.